In this module, we will introduce the root locus technique. In this module, we will first begin by reviewing the transient response characteristics of a dynamic system, and in particular how poles affect that transient response and how we design controllers to achieve a desired transient response. We will then introduce a new graphical technique for designing controllers or designing systems in general. We will also introduce an approximate procedure for drawing the root locus, and we will try and give some intuition as to where this procedure comes from. So previously, when we began to design controllers, we basically used an algebraic approach for choosing our gains. When we have a system that has a known simple form, for example, has the form of a canonical first-order system or a canonical second-order system, we can basically use algebraic relationships to choose various parameters to achieve desired pole locations and transient performance. For example, for a first-order system, we precisely know what the effect of tau is on a system's response. And so if we can relate tau to a control gain, then we can solve for tau. Similarly, with zeta and omega n, we have exact relationships for how the parameters of a canonical second-order system affect things like overshoot or settling time. And so by matching our closed-loop transfer function to this standard form, we can choose our gains to achieve certain desired characteristics. When we have a higher order system, that is a third, fourth, fifth order system that doesn't have these simple canonical forms, then it's much more difficult to design the controller. We don't have precise relationships that we've derived for capturing the speed or the overshoot of a system. We don't even have something like a quadratic formula for precisely expressing the poles in terms of our controller gains. And so it turns out that there's a technique called the root locus that can help us when dealing with these higher order systems. So the root locus is basically a graphical tool that shows how the closed-loop poles of a transfer function move as a parameter, which is usually a control gain, is varied. And so here's the complex plane, and this picture is a root locus. And these red lines show all of the locations of the closed-loop poles of a given transfer function. For example, we could imagine if k equals 0, so this is maybe a proportional control gain. The location of one of our closed-loop poles is located at the origin. And as we increase k, that closed-loop pole moves. So when k equals 1, maybe it has that location. When k equals 2, maybe it has that location, and so on. As we increase k, we can see how this pole of the closed-loop transfer function moves. In this case, we basically have 4 branches of a root locus. We have 4 lines. So this is one line, this is one line, this is a line, and this is a line. And so each of those lines shows how a different closed-loop pole moves. In this case, we have a fourth-order system. So this is something that would be very difficult to address algebraically, but by using the root locus, we can see how all 4 of the poles move as we vary this parameter k. And by knowing where the poles are, we can figure out which poles are dominant. We can figure out, are they indicating that the response is getting faster? So moving the poles to the left in the complex plane corresponds to making sigma larger, which corresponds to a faster settling time. We can see what the effect is on beta or zeta to get a sense of overshoot. things like that. And so this is very helpful for higher order systems because we don't have these precise algebraic relationships. And they're also very useful for finding approximate results quickly. So we don't have to do 2 pages of algebra to select a particular gain. We can draw a picture like this in 30 seconds. Maybe it's not exactly correct, but it gives us a rough idea of how qualitatively changing our parameter affects the location of the poles and in turn affects the transient response of our system. So here we're